begin a short set of sporadic lectures, meaning that we're not going to put them out on necessarily a regular schedule, but we're going to cover the subject of quantum electrodynamics prerequisite topics. These are the things that you need to know if you want to do a serious study of quantum electrodynamics. This is the stuff that you should have under your belt to make the journey through QED a bit more logical, right? And so instead of beginning your study of QED, beginning your study and then getting to a point where there's like, wait a minute, I'm not sure I follow this. And what you realize is you don't follow this because there's some topic out here that you never really mastered or you reviewed or learned the first time and have forgotten. So you go back to that subject, catch it up, kind of clear up this point, and then move on to the next until there's another issue that makes your life complicated and difficult. And then you have to kind of pause and take a look at that again and get it under your belt. Not a big problem, right? This is how people learn any new advanced subject, right? And then you move on to the next topic. And then there's the same process of gathering information that you never knew before or forgot. Clear that up. You should be clearing question marks up. So here's the question mark, you clear it up, and then you move on, right? And then, of course, this process never ends because QED is a pretty big subject. I mean, the core of it is there's a certain body of it that you have to decide, a canonical pedagogical body you got to capture. But, you could study the subject at any level of detail. And then, of course, once you have it, that becomes sort of a model for quantum field theories in general, right? So if you want to get to full-on quantum field theories, you've really got to go through QED, just like you've got to go through classical electrodynamics to get to quantum mechanics. It'd be sort of absurd not to do classical mechanics, classical electrodynamics before quantum mechanics. So there's sort of a standard progression. So the question is, what are these topics here? What are these guys? And there's no way of telling, right? For every person, it's different. So all I can do is I can say, well, I've seen students weak in this subject here, so let's do a lecture on that. And maybe I met a student once who had some trouble with this subject, so let's do a lecture on that. And I myself was unprepared for this topic, so let's do one like that. There'll probably be a lot of these because my journey through QED was definitely not a straight line, and I was definitely unprepared for it in the beginning. So let's begin, and I think this first thing is to really nail down the quantum mechanics formalism of the bracket notation, the Dirac formalism. I think that's critical. Everybody has some exposure to it, but having a deep understanding for the origin of the formalism, why it works, or how it works, I guess I should say. Why is always a little tough thing to deal with in quantum mechanics, or any physics really. But getting down to the basics of it, I think, is worth a lecture or two. So let's begin. So the Dirac formalism, so-called, is the formalism of the bra and the ket. And I think this is all supposed to blend together to be the bracket, right? Although you never hear it said literally as bracket. Right? So let's just erase that. So the formalism of the bracket. And this stands sort of in opposition to the wave function formalism. And so it's really important I believe it's really important to know the full link between these two. The wave function formalism is something that chemists may learn, for example, right? Chemists never really work with the bracket formalism. And also, I have some really good quantum mechanics texts, right? They're excellent texts, and they work in the wave function formalism. I must say, the more modern the text, the less it does so, the more it moves into this formalism because of the advantages of the formalism. But the difference between the two is really the level of abstraction. This is the reason why you might want to stay away from the Dirac formulation for early studies, because it's so mathematically abstract compared to anything else we've ever done in physics, right? If you've gone through, for example, if you've gone through electrodynamics, you say, oh, there's a particle and it has a charge. We'll call that charge E. And the particle is going to feel a force. And how do we know what force it feels? Well, it feels a force depending on the electric field, say. Or if you know the particle has a velocity, it feels a force related to the magnetic field as well. So in some sense, the electric and magnetic field are abstract notions of something that exists everywhere in space that defines how a particle feels a force, right? A charged particle, at least, feels a force. This, you could say this is sort of an abstract idea because you're positing sort of a mathematical quantity that exists everywhere in space called a field, and you have to introduce this into the physics. But for some reason, we don't have trouble with that. We can say, okay, I understand space, I understand math, so I understand coordinates, so I can imagine a field sort of all through space. It becomes something that we absorb quickly. That probably was not true in the pre-Newtonian era, where all of this was in question. All of this, the idea of a gravitational field was a very puzzling idea, and positing an electric and magnetic field in empty space was certainly not how it was introduced, right? They said, well, if there's going to be a field there, and the field equations, which turned out to show wave phenomenon, clearly there must be something in space to support the field, right? This was, de rigueur before Einstein. And even still, the idea of what possibly could be the sort of thing that lives in truly empty space is still a big puzzle. The point is there is this idea of abstraction, but in the modern era, we kind of lose it. We just accept fields so much that we don't even realize how, in principally, mathematically abstract they are. And these are classical fields we're talking about, right? I'm not even talking about quantum fields from quantum field theory. So abstraction's not new. It's just this is the first time where abstraction will hit a student who's already accepted this or doesn't even consider this abstract. The Dirac Formalism is the first place where just, boom, it's abstract no matter who you are. That's literally how abstract it is. The wave function formalism is less so, because the wave function formalism, if you really started it from scratch and took it seriously, really comes from the principle of matter waves, right? And you just take the idea of de Broglie, and we learn early on to accept his notion that matter has wave-like phenomenon. And from that, it's a simple jump to understand that these matter waves really represent a wave function and to sort of go off to there. But once you accept this, the wave function formalism, as strange as it is, I mean, it embodies everything about quantum mechanics. You can do all of quantum mechanics with it. It becomes a little easier to bite. The Dirac formalism, however, just takes the wave function formalism and puts it on a mathematical foundation that goes into completely abstract math. In fact, it goes literally into abstract algebra, and it makes contact with linear algebra, but abstract algebra is just the algebra of vector spaces, and the algebra of, well, algebras. Right? There's algebra. An algebra is a literal element of the notion of abstract algebra as a subject. So we're going to discuss this. We're going to discuss the Brockett formalism, how it links to the wave function formalism, and because that's what you need to know as a prerequisite for QED. All right, so we need to establish what is a vector space in a much more precise way. And by precise, I mean I'm going to talk it through, and if you really want to learn it, it's part of abstract algebra. But fortunately, a vector space is a very, very simple thing, right? It starts with, it is ultimately a set. It's a set of objects, and everything in a vector space is a vector, right? That's, if you have a vector space, its elements are by definition vectors. Now, the problem is there's a lot of vector spaces in the world of math and physics that are used that have other special names, and we kind of forget that that the elements are in principle vectors. For example, you can have a set of tensors, but a tensor product space is a vector space by definition, and the tensors that are a member of that thing are also vectors, right? You can have a covector space, and its elements are covectors, but a covector space fits the definition of a vector space, so its elements are actually also vectors. So the point is, if you have a vector space, its elements are vectors. And there's an infinite number of them. I have it written down here in a way like it looks like it's countable, but it's, in almost all cases of interest, it's an uncountable infinity of objects that live in the set. But having the set of things that you just call vectors isn't good enough. You also must have you must have a field, right? There's a field as well. Now, a field is another algebraic object that's actually more complicated. Well, that makes no sense. If you need a field to have a vector space, then clearly a vector space is more complicated than a field. But a field as an object is an important thing that is part of the algebra that construct a vector space. So you need a set and you need a field. And fields come in 3 types commonly and 5 types if you stretch it, right? So the fields we talk about is the set of real numbers, the set of complex numbers, and the set of integers modulo with some modulo arithmetic. This is a finite field, right? We're not going to talk about finite fields. And then there's also these 2 other things out there, the quaternions and the octonions, who technically don't meet the modern definition of a field. Quaternions close. They're not commutative, so fields, the elements of a field have to be commutative. Quaternions are not. Octonions are not even associative, but these guys are called division algebras, which means it has something to do with their ability to divide and not run into problems. Nevertheless, we're not going to use any of these fields. The only field we care about is the complex numbers. So when we talk about the field of complex numbers, all you have to know is you've got complex numbers and all the complex arithmetic that goes with it. That's the field of complex numbers. It's not just the set of all complex numbers. It's the set of all complex numbers with its associated addition, subtraction, multiplication, division, and all of those things. So you have a set of vectors and you have a field. Now what you need to define are some key operations. You have to be able to add 2 vectors and get another vector. So every 2 vectors can be summed to yield a third vector. It's closed under this addition operation. Now this addition operation only applies to vectors. So this is like attached to the vector space. And you could actually put, the little letter V here just to make it clear that this addition operation is only good for elements of the vector space V. The other thing you put in here is scalar multiplication. Every vector can be multiplied by an element of the field to get another vector. And you're just scaling the vector is what we say, and that's why it's called a scalar. But it's a way of taking a member of the complex vector space, a member of the complex numbers that are associated with our vector space. You got to think of it as sort of a bin of scalars, right? These are called scalars. And you have a bin of scalars and a bin of vectors. And you could take any vector and one member of the scalars, multiply them together, and you get another vector, right? So, and just as with addition, you could put a little v here to say that this is scalar multiplication for the vector space V, right? And it only applies to the field that you've attached to V. If you attach the complex numbers, by the way, to a vector space V, it becomes what's called a complex vector space. The reason a vector space is a complex vector space is because the scalars are complex. It has nothing to do with these vectors being complex. Sometimes it seems that way because when you study the subject for the first time and you run into a complex vector space for spin, you see that the elements of the objects that are used are complex. They're column vectors with complex entries. That's not why it's a complex vector space. It's a complex vector space because the scalar is a complex number. Then you have to be able to define that 0 scaled with any vector is the 0 vector. This shouldn't be, I should get rid of that little vector symbol. This is the complex number 0. I can't erase it right now because of the way the presenting has worked, but I will erase it in a moment.
So 0 times any vector is the 0 vector. What is the 0 vector? Well, the 0 vector is what you get when you add the opposite of a vector, right? So if I multiply a vector by -1 and I add, I should end up with the 0 vector. Another way, probably a better way of saying it, is that any vector plus the 0 vector is the same vector. I don't know why I didn't write it that way. That's the obvious way of defining the 0 vector. I've defined it, but this kind of kills two birds with one stone, right? Because every vector also must have an inverse vector under addition in a vector space, right? So in this case, -1 times any vector when added gives you the 0 vector. So that's another property vector spaces have to have. And what's also important is that the scalar multiplication must be distributive with the vector addition, right? So if x is a complex number, x times the vector alpha, scalar multiplication, where I've left the dot out, you usually leave the dot out, this dot here. When you add those two together, it's the same as adding the two vectors and then scalar multiplying by x. This is why it's called linear. And sometimes, as I pointed out before, and I'll say again, everything is linear. This is what makes it linear. And let's see if there's something else. Oh, and every vector space, of course, has a basis. This is a collection of linearly independent vectors that can sum to make any vector in the space. So any vector in the space can be represented as a sum of complex numbers multiplied by basis vectors, where that multiplication is your scalar multiplication, right? This guy right here. So there's an implied scalar multiplication there. And these are called the components of the vectors. This is called the basis of the vector space. It has to be chosen, but you can be chosen quite arbitrarily. The only thing that's required is that the basis of the vector space, no one basis vector, can be written as a linear combination of any of the others, where by linear combination, I mean this. So I cannot replace alpha with any of these guys and get a true statement. And the number, the thing that's unique about this is the number of linear, the minimal number of vectors that requires to do this will be the dimension of the vector space, which is another way of saying the size of the basis is the dimension of the vector space.
So now I can fix this up. We get rid of that, right? And what was the other problem? There was another problem. Oh, yeah. So these guys, they don't belong. We're never going to deal with this one. And real numbers, that would be general relativity, where the vector spaces have to be real. So we just live with the complex numbers. So when we think of a vector space, we don't even need to think of this abstract notion of the field. We just think of a set of vectors, a bin of complex numbers. We think of vector addition, scalar multiplication. 0 times a vector is the 0 vector. A vector times its inverse is the 0 vector. I guess I should write that the 0 vector plus any vector equals that vector. I guess that's what sort of defines the 0 vector. And there's only one 0 vector. You can prove that there can only be one 0 vector. The idea of linearity and the idea of a basis. So this is what a vector space is. And the reason vector spaces are important in quantum mechanics is because we are going to postulate that every physical state of our quantum mechanical system is a vector in a vector space. It's described as a vector in a vector space. So I have some state in the world, there's a vector in a given vector space that describes that state and provides us with all the information we need to know about that state. And that is the abstract thing that's hard to understand, because this is such a simple structure, right? This is really, there's not much to this. And in fact, there's so little to this that two different vector spaces, if they have the same dimension, they're mathematically identical, right? You have to start coming up with excuses to distinguish vector spaces that have the same dimension, because they're all what they call isomorphic. They're all the same. There's so little structure here, you can't even make two different ones very easily. So we're going to talk about how you can distinguish some vector spaces. But the point being that the reason this is important is that these abstract objects, these simple abstract objects, really are the foundation that allow us to create this dizzyingly complex subject of quantum mechanics, right? Every quantum mechanical state is simply one of these vectors. And that's where the Dirac formalism begins. Okay, let's quickly look at another important vector space called the dual vector space. Now, the subject of the dual vector space is a bit sensitive in the pedagogy of quantum mechanics because it's very rarely discussed in full. And because of that, when you read a paragraph about the dual vector space, you feel like you're leaving something behind. And you know the idea of dual is important because you've probably heard something about string theory and duals being really critical in string theory and things like that. So you kind of want to know, when you see this word dual, you kind of want to know what's going on. But in early quantum mechanics, they really brush this aside. And even the best books meaning Sakurai is probably like the best book, the best second quantum mechanics book you should read. And there are plenty of really good quantum mechanics books. I love Griffiths, a very beautiful book by a professor from Reed College named Griffiths, and he does a great first quantum mechanics book. But Sakurai is the definite place to go for the second, and he really spends a lot of time on this formalism. So does Griffiths, by the way. Griffiths spends some time too, but Sakurai really digs into it, and but neither of them really talk about the dual space, and I think that's a real big miss. Of course, it's a lot of extra complication, but that's the purpose of my lectures, is to sort of get it so everything here is comfortable and solid ground. So we need to know about what a dual vector space is. So let's begin. We first by taking note of this important notational step that we use in quantum mechanics, right? We talk about the vector. We give the vector a name. In this case, we're going to call the vector alpha. I'm giving the basis vectors for the vector space where alpha lives, right? So there's this vector space that includes alpha and all of its vector buddies. And the way we write down any given vector in such a vector space is we either write it down by just stating its name, right? It's a member of the space, there it is. We just assert that it's a member of the space, we call it alpha, and there it is. But if we have chosen a basis in this vector space, if we have gone out of our way and found a particular or identified a particular collection of vectors that we're going to call the basis, and I'm going to put this little arrow over the basis vectors. And if we do that, alpha, by definition of a basis, must be written in this form. Well, let me put it in this form with the sum. It's the sum over alpha, some field element or some scalar, right? The field element, the field, of course, is the complex numbers. So it's a complex number multiplied by each of the basis vectors in turn. And we usually count the basis vectors, from general relativity, I'm so familiar starting it always at 0. So I've written it from 0 to n minus 1. But this could just as well be 1 to n, right? We could do it that way as well. And for those of you joining from the What is a Tensor series, of course, this is just written in short form without the summation. So if you see up and down indices that are the same, you imply this very sum. However, quantum mechanics does not use this form, right? So I'm going to put a red X through it because do not expect to see that form in the study of quantum mechanics, and certainly in the study of this formalism. So the point is, the takeaway here is that I can name the vector, but once I have a basis, I can always write it in this basis. Okay, and if I have a vector space, we're guaranteed to have a field, right? And the field of complex numbers is something we can talk about because a vector space, by its definition, has a field of complex numbers. So the point is I should, since I have a set V, let me draw it in black, since I have a set V and I have a set C in the universe where a vector space exists, there is the potential to take any vector in the set V and map it to a complex number in the set C, right? I should be able to create a mapping. And this mapping, it seems like it might be canonical in the sense that I haven't had to add anything to my universe. I have two sets, so there should be a mapping between the sets. So I can give that mapping a name, for example. I could call that mapping omega, right? And the idea would be that if I have omega and I have a vector alpha, I should get an element of the complex numbers. I should be able to get a complex number. I could call that complex number, say, z, right? And z is a complex number. So having two sets means you can talk about mappings between the two sets. And we do have two sets. I have a vector space, which means I have a bin of scalars, a complex number scalar. So I should be able to talk about mappings between that vector space and the complex numbers. And how would I construct such a mapping? Well, with all of this stuff is if you've chosen, in order to make an explicit mapping between V and C, I have to be able to get my hands on a vector in V. And the way we say that is I have to choose a basis in the vector space. And if I choose a basis in the vector space, then I can define the map W by how that map acts on just the basis vectors. And then we'll see, once we've done that, we've done it for everything. So, for example, if I take the basis vector E0 and I define as omega of E0 the number 5, right? I'm now creating a map, right? I'm creating a map that, well, it doesn't tell me everything, but it tells me at least how E0 maps to the complex numbers. 5 is a complex number. You know, nice real one, but it's a complex number. So I could do this for then E1, and I could say, oh, E1 goes to the complex number 3 plus 2i. Now, obviously, I'm picking these arbitrarily just to show you how flexible this process is. There's no constraint on what complex number I choose, right? If I do this for E2, say 15 plus root 3 pi times I, right? Root 3 times pi times I, right? That's a complex number. So I've just said E2 maps to that thing, right? And I do this for every member of the basis. And here, for the last one, E sub n, it went to negative 100.2 for some reason. So once I've done this, then all I need to do is remind myself that, hey, alpha simply equals the sum from 1 to n minus 1 of alpha I, E, I, right? And this, if I pick a vector in the vector space, right, if I pick alpha, that's akin to defining these alpha i's, right? I know what these guys are. If I have one particular vector and I've chosen a basis, picking a vector is equivalent to picking these EIs. I've already chosen the basis, so I have to pick these alpha i's, not EIs, alpha i's. EI is picked, right? We establish some basis. And this is a very important subject, right? Establishing a basis in a vector space, that requires care and thought and intention. And quantum mechanics is all about choosing these bases. We're going to see that this is a big step. Choosing this basis is what makes quantum mechanics work, right? But we're speaking in abstract terms now. This is abstract mathematics, right? So any basis that we choose, if we call those basis vector E sub I, and we claim that we've pulled out a vector from the vector space, that means we know the coefficients, the field values, the complex numbers A sub I that make up this vector. And in fact, we could write that down. We could write down that equals alpha 0 E 0. I know I'm going to be really sorry that I'm starting at 0 here. Actually, that should have been a 0, right? If I go to n minus 1, that should have been a 0. Plus alpha 1 E 1 dot to alpha n E n, right? And this is alpha. Now this mapping, if we presume it's linear, right? Maybe I should write down linear mapping because that's what we want to talk about. So I'm now going to say, oh, the mapping omega acting on alpha, because it's linear, it's going to be alpha 0, which is a complex number, so that should come out, to the mapping of omega on E0 plus alpha 1 times the mapping of omega on E sub 1 all the way to alpha sub n times the mapping of omega on E sub n, right? And the way we defined our mapping, we've defined it for the basis, right? We've defined what omega does for each of these basis elements, right? That is omega e sub 0, right? This is omega e sub 0. This is omega e sub 1, right? All the way down to omega e sub n, right? So we've defined it for each of those things. And once we've done that, I just take these numbers and replace them right here. We know alpha 0, we know alpha 1, we know alpha n, so I can multiply those two complex numbers, multiply those, I can add them all up, and what do I get? I get some number z, which is an element of the complex numbers. And that is how you create a mapping from V to C, right? You choose the mapping for the basis. Well, V now we presume to have a basis. We create the mapping for the basis explicitly and discretely, right? And then we pick out our vector and we execute the mapping on the vector. We have to understand that it's a linear mapping. So when I say linear, what I mean is omega of alpha plus beta, where alpha plus beta are two vectors, that's going to be omega of alpha plus omega of beta, right? So that allows us to apply omega to this, right? And then write it as omega alpha 0 E0 plus omega alpha 1 E1, etc. And then because it's linear, it's also true that omega of a complex number z times a vector alpha is going to equal z times omega of the vector alpha, right? And that allows me to take the alpha 0 and bring it out front, the alpha 1 and bring it out front. And that's where these terms all come from. So that's what linearity is. And linearity is absolutely crucial. You have to have this all be linear or it doesn't make any sense. Okay, so that is how you create a mapping from your vector space to the complex numbers. So now, why is this important? Because remember, our goal here is to talk about the dual vector space, right? The dual vector space. And all I've talked about is mappings from the normal vector space, the underlying vector space, to the complex numbers. So what is this all about? How is this relevant for the concept of the dual vector space? This is like prerequisite to the concept of a dual vector space, I guess. All right, so let's talk about that. All right, so let's back up. We've cleared the screen. We understand those points. So now we're going to try to get to the bottom of what this dual vector space is. So here's what we've got. We've got ourselves a vector space. The vector space, we have established a basis. It's over the complex numbers. We're only going to talk about complex numbers in this course. Complex vector spaces. By the way, if you have complex scalars, that is what we mean by a complex vector space. That's really important because sometimes people think, oh, complex vector space means the vectors must be complex, and that's not true. Complex vector space means the scalars are complex, right? Okay, so we have this dual complex, or we have the dual vector space that we're after. So we've described the idea of how to construct a map from V to C. But what we noticed is that this map was pretty arbitrary. And I want to ask the question, is there a canonical map? And I love this word canonical because it's thrown around and it really kind of twists students' heads in the beginning. What do we mean by a canonical map? And canonical, I've kind of parsed how people use this word most often, and this is what I've come up with. Canonical means it's forced upon you, right? That means you don't have to think about, well, you have to think, but you don't have to do anything special to create something. So, for example, once we have a vector space, is there anything that forces one particular map omega on us? Is there anything that says, hey, there's this, yeah, you can make maps arbitrarily from V to C, but there's this one map that's like special, that stands out, that we all need to be aware of because it pops from all the others in some way without adding any new elements to our vector space or any new properties or any new principles. This one map jumps out at us, right? And here's like a candidate for that kind of thing. I'll show you. So if we started, we're going to define, we're looking for one special map, right? Well, one special map means one particular mapping of these basis vectors. So the first problem, of course, is that choosing a basis is a very flexible procedure, right? So, but we're assuming we've done that. So let's assume we've chosen a basis. Is there a map that jumps out? Well, you might say, well, yeah, there's a map that jumps out. The map where all of these guys are mapped to the number 1, right? These are the basis vectors after all, right? So if I created a map, I could map, if I created a map omega, I could map e sub 0 to 1, to the number 1. I could map e sub 1 to the number 1. I can map them all to the number 1. That jumps out at me. And, okay, the problem, of course, is that, geez, I could also just replace that. If mapping things to simple numbers is our game, why don't I just map them all to 0, right? Well, that's even simpler, right? The mapping of every single vector in the vector space would go to 0, right? So that seems pretty canonical in a sense. But the truth is none of these are canonical, right? My choice here is completely unrestricted, right? I might prefer 0, I might prefer 1, I might prefer 10. There's no way of establishing some mapping here that we can say is forced upon us by the existence. It jumps out because of the existence of the vector space. And so the answer to is there a canonical map is really no, right? Until it's a little subjective, right? Maybe ones do jump out at you and you feel like that's canonical somehow, but it's not considered that by the general practitioners of the field. And so the answer here is actually no. There is not a canonical map. So, tough luck, right? We know maps exist, but there's not a canonical one. But that doesn't mean there isn't a canonical object in play here. And the canonical object that is in play is if we cannot pick a single map that is canonical, we can say that the set of all possible maps, right, that is canonical, right? I mean, it seems like a cop-out, but it is possible that if I take the set of all possible maps, it is possible to collect them together. Well, let's see. If I take the set, collect them together, that's sort of redundant, right? If I take all possible maps and collect them together into a set, meaning every possible choice that you could make for these numbers here, every possible choice, I could throw that all into a set, and that's a thing that would exist, right? Because we know V exists, we know C exists, and therefore it is true that mappings between two sets exists. I can't pick one of them out and call it canonical, but I can create a set of all the possible maps, and that would be canonical. That does pop into existence. That complete set of all maps does pop into existence as soon as we create a vector space. Because as soon as you create the vector space, you have C, you have the set V, and therefore you have you have the possibility of mappings. You can't dig one out, but you can put them all together in a set. And that set we're going to call V star, right? We're going to call that set V star. And that set is the dual vector space to V. Now, we haven't shown that this set is a vector space, right? All we've done is lumped things together into a set, and a set is not a vector space, right? Because in order to be a vector space, you need these parts, right? You need this addition, you need this multiplication, you need to have these identities be true, you need to be linear, all that stuff. We haven't created those pieces for this dual space. All we've done is gathered up a bunch of things. That's not good enough. We have to gather up a bunch of things and give it those addition properties, the scalar multiplication properties, and all those other things before we can call it a vector space. But notice that This vector space, the underlying vector space, is purely abstract. We're just listing elements. The element A, the element alpha, beta, gamma, and all of its infinite associates. All of its scaled associates, meaning all those things multiplied by C. Basically, all of these guys, all of these basis vectors, right, multiplied arbitrarily and added arbitrarily, multiplied by C, the scalar C's. Let me put it this way. All the basis vectors arbitrarily multiplied by an arbitrary scalar and then arbitrarily added together produces this infinite set of objects. And all that is an abstract collection of objects defined exactly the way I've defined it. This is very pure mathy stuff. On the other hand, this is a little more tangible, right? Because this says, well, what I do, I'm a machine, right? I'm a machine. Omega's a machine. You give me one of these super abstract objects and I return a complex number. So it's like this, it's like the vector space or the dual space is a little less abstract than the underlying vector space. The underlying vector space can literally be treated as a massive bunch of symbolic manipulations, right? And which is hard to believe that that's going to be the architecture that we rest quantum mechanics on, but it is. But this guy actually looks like a bunch of little tools whose job it is to take a vector v and return a vector c, right? So in some sense, the dual vector space, which somebody might think is, oh, that's pretty abstract stuff. It's actually a little less abstract in some sense than the underlying vector space. But let's talk about why we're calling it the dual vector space. Well, first thing we need to be able to do is, let's say I have an element omega of the dual space, right? It's a map, the map omega we talked about. And then say I had another map. I'll call this map omega 1. And then, well, I better not do that. I'll call it omega, and then I'll call another map gamma. I have to create a third map that logically makes sense of the addition of two maps, right? So this third map, which I might be able to call omega alpha, I'll call the third map delta, right? So these are now all members, omega, gamma, and delta are all members of this dual space. So they're all maps, right? So now I'm talking about I need a way to take a map and add to it another map and get a map, right? Because that's the rule. The rule is this addition takes two members of a set and returns a third member of a set. And that's the first step to becoming a vector space, is to have that kind of addition. There's other steps, but that's an important step. Well, if this is a map,
So if the left side here is a map and the right side here is a map, and this is an equality of maps, well, what do maps do? Well, maps take vectors and return real numbers. So I can actually consider the left and right side as functions of a single variable where that variable is a member of the vector space V, the underlying abstract vector space V. So the way I write that down is omega, I guess omegas should have a little thing there to make them look a little more Greek, because I might want to use W's. I think I'm going to go with like Roman letters for things in V and Greek letters for things in the dual space, although I started the other way around, but be flexible, right? Gamma, and then there's a slot here. There's like a function slot here, and then this is delta. Delta is a map, so it takes a vector too. And in that function slot, I am going to put a vector, which I'll call x, the vector x, right? So x is an element of the underlying abstract vector space. So these maps are linear, right? So I need to know what number, and they return a member of the complex numbers, right? So the result of this has to be a complex number, and obviously the result of this has to be a complex number. This we call a dual space mapping, by the way, right? A member of the dual space operating on a member of the underlying abstract vector space produces a complex number. This process is the dual space mapping. Now remember this, because our extra level of depth in understanding this critical topic really is going to center around some language and some shades of difference between a few things. Anyway, the left side and the right side are both complex numbers. Now, the left side, we can exploit the linearity of the maps. and we can say whatever that complex number is, it's the same as W acting on the vector x plus gamma acting on the vector x. So the map W, so this is now going to be a complex number, and this is going to be a complex number. So addition here is no longer the addition of two maps. The addition here is now the addition of two complex numbers. You almost have to keep track of this, right? Like I could write, if I wanted to back out of this, I could write that this addition is in V star, right? So I create a new symbol because addition symbols come up everywhere, but I need to know what's being added. So if I do this, I say, yeah, we're talking about the addition of two members of V star. That's what we're trying to define here. But once I go to this mode, omega x plus gamma x, now I'm talking about addition in the complex numbers, right? And on the right side, I get delta x. So now this is easy, right? I now define delta x is the map that returns the same complex number as when I add the individual mappings of omega and gamma. And that does it. That defines this guy. And if I define this guy, I've created my notion of addition, right? So we can add two maps, and we now have addition, right? So now we have to, what else do we have to have? Well, we have to have scalar multiplication, right? Which is a map from the complex numbers and the dual space, right, to a member of the dual space. So I have to be able to take a map from a map who takes vectors and returns complex numbers, and I have to return another map after scalar multiplication by a complex number. And that's just really easy because what we're going to say is that if I have a map gamma, right? I know how gamma operates. Presumably, I know how presume that I know how gamma operates on omega. Well, how do I know exactly how it operates on? Well, omega. I shouldn't be using omega, right? I've decided I'm going to use so the vector x, right? So x is in the underlying abstract vector space, and gamma is in this dual space that we're also trying to show as a vector space. So I have to define this operation of scalar multiplication of dual vectors, right? And this is a very simple process, right? I know how gamma acts on x, presumably because I've defined it for E0, E1, E2, right? I know how each of these maps into a complex number, say Z1, Z2, I guess Z0, Z1, Z2, and Z3. So, I've done all that work, so I know how this guy operates. And now I say, well, what I want a complex number times that to mean, this is now a complex number, right? I want that to be just the complex number times the mapping. Or, equivalently, I want it to be the mapping of the complex number times the vector. Remember, we know how this is now scalar multiplication in V. This guy is actually scalar multiplication in V star. So I'm defining scalar multiplication in V star in terms of scalar multiplication in V, right? So scalar multiplication is not a problem. That'll work just fine. It's linear, so I've already shown the linearity. The identity map, the identity map would be, let me erase a little bit. The identity map is just the map that takes all the basis vectors to 0. And if we use the addition in V star property that we've just defined, you'll see that it returns the same map. So that's good. And then every map has its opposite, right? If I define this with, say, Z0, Z1, these are all complex numbers, to Zn. If I just switch the sign of them, you can see that if omega is defined with the positive sign, and then minus omega is defined with the negative sign. And minus omega does equal the number -1 as a complex number. Scalar in V star times omega, right? Those things are the same. So all of this works, and we have all the properties of a vector space. So we now can talk about the dual vector space is this set of all possible maps with these kinds of addition rules and all the addition rules and the scalar multiplication rules that we talked about. Okay, so why is this? So where does this leave us? Okay, so now ultimately quantum mechanics is going to rest on identifying all physical states with a vector in a complex vector space. Period. And full stop. That is how the theory is constructed axiomatically. Axiomatically, that's how it's constructed. But what's important is once we postulate the existence of any abstract vector space, we automatically and canonically create a dual space. It has to exist, right? That set of all possible maps definitely exists, and there's a very logical addition in V star. Right here, there's an addition in V, but there's an addition in V star. There's a scalar multiplication in V star. I'm going to drop these subscripts on these operators pretty soon, but I just want to point out that they're in different spaces, right? They mean different things, and there is a basis in V, right? So likewise, there is a basis. V star is a vector space, so we can have a basis too. I'll call the basis vectors in V star, I'll call them omega with a superscript I, right? So that's a little bit of general relativity slipping in here, right? Where basis vectors of the dual space are given superscripts to identify them, and basis vectors of the underlying abstract space are given lower indices to describe them. And likewise, a vector x, if x is an element of the abstract vector space, a vector x is written as the sum over I of x superscript I with the basis vector ei, where this is a complex number that's the component in the description of this vector x in this particular chosen basis, right? And likewise, a member of the dual space, omega, which is a member of the dual space, omega is written as the sum over I of, I guess, w with a subscript, and I guess I shouldn't use omega because omega is what I'm using for the basis, right? So let's say alpha, Greek letters here. We'll use Greek here and Roman here. So alpha is going to be, alpha is going to be alpha subscript omega superscript. Now omega is still a vector, right? So this little symbol here, that means it's literally a vector, right? This is a vector space, so its elements are vectors. We call them covectors because we want this space to sort of be our true vector space. This is the space we postulated the existence of, right? This is the space that's got all of the states of our system, right? So this is the state that quantum mechanics is built off. So we're going to call that the underlying vector space, or the underlying abstract vector space. I've been trying to come up with all kinds of words for it. This is usually called the covector space only because of its relation that it popped into existence, the set of all possible maps. It's canonical. It pops into existence only after we describe this. However, it is a vector space in the abstract math definition, and as such, the elements of it are vectors, right? So there is this language issue where, the elements of this space are vectors, the elements of this space are vectors. But when you have them together, we tend to call these guys covectors or dual vectors, right? But it's also true that vectors are dual to dual vectors. In other words, if V is a vector space, right, then V has its own dual, right, the double dual. And it turns out the double dual is actually this vector space itself, right? So the double dual of V equals V, right? Anyway, I don't want to get too far off down there, but the language is a thing that causes trouble. Anyway, where was I? So the point is once we speculated on, or once we assign this as going to do the job of creating quantum mechanics, right? We're going to create quantum mechanics off of this thing. Then this thing automatically appears, right? You can't get away from it. And I guess I didn't say it, but the dimensionality of this mapping space, if you look at how we constructed it, you'll see that it has to equal the same dimensionality as the underlying space. Now, there is the question about infinite dimensional vector spaces. I'll talk about that in the next lecture, probably. It's an important point, but I need to get through some other stuff here. Okay, so now we have these two things that exist when we are making quantum mechanics. Let me erase some stuff. Now we need to think about a very interesting question, right? Let me draw this. See the circle? This circle is the set of all vectors in the vector space V. And this circle is the set of all the dual vectors, right? Now, there are some special vectors in V, right? There is the zero vector. Every vector space has one. Likewise, there's the zero vector in this vector space, right? So if now we're in a position to ask another question. We've already shown that just because complex numbers exist and the vector space exists, we can make maps from the vector space into the complex numbers. And that analysis spawned this entire separate vector space, right? Well, okay, if that's true, if all I need are two sets to create a bunch of maps, well, now I've created another set, so now I'm going to have to create another bunch of maps, right? Right? I can create a map from V to V star. So there should be maps between these two vector spaces, right? Which means I take any vector in this vector space, I should be able to find a vector in this vector space, and the mapping that should get me from there to there, I'll call it capital omega, right? So now we ask our question, all right, such a map could be defined. How might we define such a map? Well, as always, we define it on the basis vectors, right? So the basis vector E0, the basis vector E1, the basis vector dot En. If I can say, well, where does that basis vector go, right? If that basis vector lives in here, actually, why don't I just draw it in there? Here's the basis vector, I'll call that E0. Where does that basis vector go in V star? Well, notice I could say, well, V star has a basis, right? Omega 0, omega 1 to omega n. Oops, superscript. And these are, I'll put little vector symbols in there. Why don't I just graph it to omega n, or omega 0, right? That sounds really logical. Of course, it is fine, right? It's a mapping, and it will work, right? If I take then, E1, right? So E1 to omega 1. I do this for all the basis vectors. That will definitely be a legit mapping. And ultimately, I'll be able to take any vector in V and map it to some vector in V star. So this is a vector in V, gets mapped to a vector in V star. Omega does it, right? I'll have no trouble with that mapping. The problem, of course, you could probably see is there's no particular order for this. Like, I could renumber this without any trouble. I could renumber 0 as 2, 1 as 4, and n as 0, and renumber all of them. And now all of a sudden this mapping is suddenly different, right? That becomes omega 2 and that becomes omega 3. And it's still legit, right? It's still a legit mapping, but it's not the same. And it was very dependent on my arbitrary selection of the order of this basis. But even worse, I could have just, what if I had just used a different basis, right? What if instead of omega, I had F? 0 and F1, right? Well, a totally different basis, so that, the way bases work is F0 is some combination of the omegas, right? I guess that'd be F1 or F0 omega 0, F1 omega 1, right? You write the new basis in terms of the old basis is what you're doing. That's another whole subject, but the point is I could have chosen any basis, and then all of a sudden these guys would have been F and F, right? So it's not obvious that there is a forced way to do this. There's not just one map. There's an infinite number of maps. I guess that's not too hard to appreciate. But what's hard to appreciate is that there's no single map that's favored. We're back into the same situation we were before when we were talking about maps from V to C. Yeah, there's plenty of maps. There's an infinite number of maps, and none of them are favored, right? None of them are favored. So how do we establish a correspondence between vectors here and covectors here? And the answer is you can't, right? You're in the same boat, right? You could create a set of all possible such correspondences, but that doesn't get you very far. Here it actually created a whole new vector space, but we need to somehow tie these vector spaces together a little bit more. And the answer is you can't. You cannot do this. You cannot find a canonical mapping between V and V star, right? Every mapping that you might propose between V and V star, you're adding some opinion to the matter, whether it's you're choosing the basis or whether you're saying, I want to take E0 to the mapping that takes E0 to 1, right? This is a mapping omega that takes the vector E0 to 1. Well, I want to map E0 to that mapping, but this is still an arbitrary choice, right? If 1 is convenient, believe me, it's not a bad thing, but it's still an arbitrary choice. So the point is there is no way to choose one particular mapping between V and V dual that stands out from all of the others. So what are we going to do? Because we need such a thing. It turns out quantum mechanics absolutely needs such a thing. So what we're going to do is first I'm going to now recast all of this in the notational language of quantum mechanics, and then we're going to address this problem. Okay, so here's where we're sitting, right? We're sitting with our vector space and our dual space. This is the guy that's going to be used to construct quantum mechanics, right? This will hold all possible physical states of some quantum mechanical system, right? And quantum mechanical system is basically a way of saying the problem you're studying, right? Whether it be the motion of a single particle in some potential well or free in space, or two particles like an Abel experiment where one's going one way and another's going the other way, and they have spin and mass and speed and all these cool things. The double slit experiment is a quantum mechanical system, all this stuff. Any one of those things, we are going to model all of the states of any system that's under study, simple or complex, by a quantum mechanical vector space. Now, there's a lot to that. There's vector spaces that are tensor product spaces that can be used to assemble a larger system from smaller systems. We're not going to talk about that yet, right? We're just focusing on the core formalism. So what's interesting is sort of clearly there's not a lot of symmetry the way I'm talking about between these two things, right? This is what quantum mechanics is rest on, and this is something that also exists, which is a bunch of maps that operate on these things and return complex numbers. I guess I should have included the complex numbers here. So there is symmetry between these things, but we lean on this as our foundation, right? And ultimately, okay, well, let's just get right to the literal formalism. How do we write this down in quantum mechanics? The way I've written it so far is abstract mathematical notation. And by the way, look at the few things you need. This will hold all possible physical states of some system. Well, this thing that does that has nothing more than a set of arbitrary symbolic things that are expressed as linear combinations of these n symbols E sub I, right? And that linear combination is driven by the complex numbers and scalars, right? So, it's got that scalar multiplication and that vector addition. Likewise, there's scalar multiplication and vector addition over on the dual side. It seems like, well, how the heck could that possibly be the case? Well, let's first get into the notation. So the way I've drawn it so far, this is very much abstract math notation, and is also common notation for general relativity. They kind of sort of stick with this notation a little bit, although even they get away from it. But the way we're going to draw this now is we're going to start making this look like quantum mechanics by the basis vectors EI, right? We are going to write them as a ket, right? And this is called a ket. And the idea is you could write this a lot of ways. You could write this as EI ket. This would represent a vector in the complex vector space. You could write it with just the I, right? The presumption might be that the ket with the I is one of the basis vectors, right? If you had an arbitrary vector in V with a name, say, I want to be a little careful on how I name things now, since we're actually beginning to talk about quantum mechanics. Let's say I name this vector, the vector in there A, right? That's the name of the vector, and there it is. It's A, just sitting there, right? Well, that's the name of the vector. Well, how would I identify just by looking at it that it's a vector in any vector space? I might put a little vector symbol over it. If it was in a textbook, I might make it boldface, right? But what we do is in quantum mechanics is we just throw it in a ket, right? That is the ket whose name is A, right? It is the state A. It is the quantum mechanical state of some system A. Or I should put it is the state of some quantum mechanical system called A, right? Remember, this is going to be the set of all states possible for a given system. Well, one of those states happens to be named A, and this represents that particular vector in this vector space assigned to the state A. Fair enough? Okay. Now, we don't need to specify A right now because we're so darn abstract. But by now, you should be understanding that you can't, despite the fact that A represents a particular state of some quantum mechanical system, and it contains all the information about that state. That's another way people say these states are. These states contain everything you need to know about A. But I just showed you, my God, look how simple this thing is. How could it contain anything? Surely there must be something I can put over here that contains all kinds of information about the energy, the momentum, the location. It contains all kinds of information about the spin, the charge, all these facts about a quantum mechanical system that we would study. Somehow there must be a thing there that this is equal to. And no, that there isn't, right? This stuff enters the theory through the operators, the observables and the operators, and that we haven't talked about yet. We're only just beginning to build this theory. Right now, we just need a thing that we can name as a state and understand that it has the properties of a complex vector space. This does not exist. The only time you will ever see a ket equaling something is when there's actually another ket over here, right? So this ket will equal something, and that thing better be a complex number, right? Because the only thing you know how to multiply a ket by is a complex number, right? That's the only thing. Complex numbers are scalars, and we've defined scalar multiplication. So whatever this is, it's got to be complex, but it still doesn't help with the whole, it contains all the information thing, because it's just equal to another ket, right? And usually there's going to be some kind of sum here, by the way. So So keep that in mind. This is how abstract this stuff is right now, right? It really is meant to be this very abstract way of naming these states. Okay, so these are called the ket states. So we no longer use this. We're going to now use, I'm just going to go with that for now. That's our basis set. And I goes from, I'm just going to take I from 1 to n. In quantum mechanics, they don't start at 0 so much. 0 is preferred in general relativity because it's comfortable to call time 0 because time actually enters the theory of general relativity differently from space. In quantum mechanics, you don't have that issue because time is just some parameter and space is, another physical observable. So they're fundamentally different. They don't really appear in anywhere similar ways. So you don't need to distinguish it from the basis vector. So our I is going to go from I equals 1 up to n, an n-dimensional vector space. And keep in mind, n can be infinite, and it can be countably infinite or uncountably infinite. All of these rules apply for countably infinite and uncountably infinite vector spaces. And when I say all these rules apply, that means I'm not going to be mathematically argumentative about it. In other words, there are plenty of mathematicians who have their reservations about infinite dimensional vector spaces. But, given the axiom of choice and some other facts, you can still presume that we can come up with a basis and the basis is orthogonal. We'll talk about orthogonality later, but you can come up with an independent set of vectors that will be infinite. The basis itself will be infinite, right? That's what infinite dimensionality means, is it takes an infinite number of linearly independent vectors to produce a sum that will give you every possible vector in the vector space. We'll focus on that a little bit more later. But the point is we're changing the appearance of things. Kets are now the vectors here. So obviously, if we change it here, we should change it here. And over here, what we're going to do is we're going to call these guys the bras. And we're going to give them a symbol like this, right? And the basis vectors of the bras will be given the opposite, sort of the reflective symbols of the kets. And so omega I, which was a dual vector, will now be, and when I say equal, what I probably should put is defined as, right? 3 bars, right? Is now going to be equal to, well, let's see, I'll make it a J, and it'll look like that. So any dual space map would be, say I had a dual space map that was given the name alpha, right? That represents the vector in the dual space that's alpha. And if we name this dual vector alpha, we know that it can be given as the sum over J of alpha. Actually, it would be like alpha J. Whoops, this is a dual vector, right? So it's alpha J, right? This is how you write an arbitrary vector in the dual space. Now notice that this is a lower index here, and I guess we should make sure we write the equivalent expression for a ket. So a ket state A, right? And I'm using Roman numerals for ket states and Greek letters for bra states. And that is the sum over I of A, I. So what have we got? We've got the basis vectors are labeled here this way. We've agreed that is our basis set. We've described how they are. There's I basis vectors. This could be a sum to a finite number. It could be a sum to an infinite number. We'll see both of those as we study quantum mechanics, or I don't know how much we're going to study quantum mechanics in this prerequisite course, but it could be either way. But notice we no longer have this Einstein sum convention, right? We no longer have AI, EI for your general vector and alpha J, EJ for your general covector, right? We don't do this ups-down Einstein sum anymore. That's purely general relativity. and we're not going to do that. So these are the way, this is the way we write a general vector, which we call a ket, and it's written, this is the ket in the basis I with components ai, and remember, every one of the a sub I is a complex number, and this is the way we write a general dual vector, also known as a general bra, written in the basis j with alpha j. Now, the next lecture, what we're going to do is we're going to talk about this correspondence, this thing that I said we can't do, or we can't connect a particular bra with a particular ket. There's no canonical way of doing that, and that still hasn't changed, right? There is nothing about what we just did. All we just did is apply symbols. We if this was a video game, this would be called a skin, right? We've skinned our character with a new appearance. That's all we've done here, right? This is all, I don't even want to call it formalism, but it is formalism. It is the formalism. So now we've got sort of the language and the notation we're going to use. So the last part of this, before we move on, it's getting a little long, but what about if I have a dual vector that that I now know is named alpha, right? I have a dual vector named alpha, and I have a regular vector named a, right? Well, I'm getting a little ahead of myself here. I have a dual vector named alpha, and I want to operate on a vector named a, right? Meaning I want to execute the dual space mapping, right? Remember, these guys take vectors and return complex numbers, right? So I know if this was before, we would have gone alpha of a is an element of the complex numbers, right? And we might have said alpha of a equals the complex number z. Well, the new, this bra-ket notation kind of lets us, that's one of the whole points of it, I suppose, is it now lets us write alpha a equals z, right? This is a dual space mapping, right? It is a dual space mapping. It is a dual space mapping. And I'm writing this out because anybody who's worked with this formula a little bit is saying, whoa, that's not a dual space mapping. That's an inner product, right? It's an inner product. Now, first of all, the inner product and a dual space mapping are not the same thing. They're not the same thing. So the next lecture, we are going to see what's going on here. But I want you to understand this as a dual space mapping, right? And that's where we're going to leave it for now. So I'll see